Our today's lecture is on light emitting diodes. In the previous lecture, we discussed photodetectors. Today, first, I'm going to introduce you to light emitting diodes. Then we will discuss energy band diagrams of semiconductors. Then I will talk about direct and indirect band gap semiconductors, followed by a discussion on PN junctions, current voltage characteristics. Then we will discuss some light emitting diode structures. And finally, we will talk about light emission characteristics. Light emitting diode is a semiconductor device in which we see the emission of light because of a recombination of electrons and holes. Now, this could occur because of two phenomena. It could occur because of photoluminescence, or it could occur because of electroluminescence. In photoluminescence, we actually have a light source, for example, laser. And if the band gap of the light source or laser is greater than the band gap of the semiconductor, if the energy of the laser is greater than the band gap of the semiconductor, it's going to result in the generation of primary electron-hole pairs. And then with the passage of time, these electron-hole pairs actually recombine, resulting in radiative recombination or in the emission of light. And this is what we see in the photoluminescence tool, for example, here at our Center for Advanced Electronics and Photovoltaic Engineering. Another phenomenon is electroluminescence, in which the generation of electron-hole pair actually occurs because of an electric source, because of electric current. And these electrons and holes then recombine, resulting in the emission of light. The application of LEDs range from traffic signals to LED texting to huge displays to LED headlights or LED brake lights. Here is another example where we see a lot of LED displays in Times Square, New York City. Other applications of LEDs include communications, for example, street light hotspots, or vehicle-to-vehicle light communication, variable light emitting diode communication, or indoor communication and navigation. Another futuristic application of light emitting diode is car-to-car communication in order to avoid, for example, side swiping of cars, or in order to avoid collision of cars. And then these cars could also communicate using light emitting diodes called optical wireless communication. A light emitting diode is made up of fundamental element called the PN junction diode. Like the PN junction is a fundamental block of light emitting diode. It's also a fundamental block of other semiconductor devices, for example, solar cells and photodetectors. So because of that reason, first I would like to talk about some of the basic concepts of a PN junction diode before diving deeper into the discussion of light emitting diodes. So consider a silicon crystal lattice. Silicon has 4 atoms in its outermost shell, and it forms covalent bonds by bonding with its 4 neighboring atoms, its 4 adjacent atoms. Now, at absolute 0 Kelvin, all these electrons in their outermost shell are actually connected to their parent atoms. And in terms of the energy band gap, we say that at absolute 0 Kelvin, the valence band is actually full of electrons, and the conduction band is actually empty of electrons. In other words, we can say that we don't have free carriers, we don't have free electrons moving around inside the semiconductor at absolute 0 Kelvin. However, with some sort of either thermal energy or light energy, we can have excess carriers. If the energy of the photons is greater than the band gap of the semiconductor, it's going to result in the generation of electron-hole pair, or it means that an electron actually transitions from the valence band to the conduction band, or this could also occur because of thermal energy. In the semiconductor crystal lattice, we say that if the thermal energy or if the light energy is enough to break this bond, now this electron is free to move around inside this semiconductor. And it leaves behind, because of breaking of this bond, it actually leaves behind a vacancy. And that vacancy is called a hole. Here is how a hole actually moves around inside a semiconductor. So consider that this bond is broken. An electron is free to move around inside the semiconductor, leaving behind this vacancy. We call it a hole. So an electron from an adjacent bond can actually jump over here, filling this vacancy, leaving behind another vacancy. So the hole actually moved from here towards the left over here. Then there is a possibility that another electron might jump from the adjacent bond, filling this vacancy but leaving behind another hole. So this process continues, and this is how the hole moves around inside this semiconductor crystal lattice. Then another possibility is that if there are free electrons inside this crystal lattice, then an electron could actually jump over here, filling this vacancy, recombine, resulting in the annihilation of this electron-hole pair. And in terms of the conduction band and valence band, we can say that an electron actually jumped from the conduction band to valence band, resulting in the recombination of these carriers. And this recombination can result in radiative recombination, or it can result in the emission of a photon. The distribution of carriers in the conduction band and the valence band. Consider once again a semiconductor. It could be silicon or any other semiconductor in which we have a valence band and we have a conduction band. So assume that with some sort of thermal energy, for example at room temperature, we are going to have a certain number of holes and certain number of electrons, certain number of holes in the valence band and certain number of electrons in the conduction band. Here is the density of states of the electrons in the conduction band and holes in the valence band. So as we can see from this plot, the density of states of electrons in the conduction band actually increases as we move higher into the conduction band. Similarly, the density of holes in the valence band actually increases as we move deeper into the valence band. Here is another plot of the Fermi-Dirac probability function, or the probability of electrons in the conduction band and valence band, and also probability of holes in the conduction band and valence band. For electrons, we see that the probability that an electron occupies a state actually increases as we move from the conduction band to the valence band. It increases from 0% high into the conduction band to 100% deeper into the valence band. Here is another plot of the distribution of carriers in the conduction band and valence band. Here is the plot for distribution of electrons in the conduction band, and here is the plot for the distribution of holes in the valence band. As we can see over here, that the electrons actually do not occur just at the conduction band energy level, or the minimum of the conduction band energy level. Similarly, the holes actually do not just occur at the top of the valence band. They have a certain distribution, where we also see a certain peak distribution, which is close to the valence energy level, but it's not exactly at the valence energy level. Similarly, this peak distribution of electrons is close to the conduction band, but it's not directly at the conduction energy level. It's around half kBT away from the conduction energy level. Consider the semiconductor energy band diagrams. We consider intrinsic semiconductor, N-type semiconductor, and P-type semiconductor. For intrinsic semiconductor, the Fermi energy level actually lies in the middle of around the middle of the band gap of the semiconductor. This depends on temperature as well, but roughly we say the Fermi energy level for intrinsic semiconductor occurs around the in the middle of the band gap of the semiconductor. And also in intrinsic semiconductor, the number of holes in the valence band is equal to the number of electrons in the conduction band. And this actually happens at a certain temperature, for example at room temperature. Consider the example of silicon. In silicon, at room temperature, we have around 1.5 into 10 to the power of 10 holes in the valence band and 1.5 10 to the power of 10 per centimeter cube electrons in the conduction band. Now consider an N-type semiconductor. In an N-type semiconductor, we introduce donor levels close to the conduction band in the semiconductor. And at room temperature, we have majority carriers electrons and minority carrier holes. We have more number of electrons in N-type semiconductor as compared to number of holes. Similarly, in a P-type semiconductor, the Fermi energy level is close to the valence band, which means that we introduce acceptor levels close to the valence band in a P-type semiconductor. The majority carriers are holes and the minority carriers are electrons in a P-type semiconductor. Another possibility is degenerate semiconductors. So we know there are lightly doped semiconductors and there are heavily doped semiconductors. Any doping level below, roughly below 5 into 10 to the power of 17 per centimeter cube would be considered lightly doped, and above 5 into 10 to the power of 17 per centimeter cube would be considered heavily doped semiconductor. And then we previously discussed in slide number 13 that in an N-type semiconductor, the Fermi energy level is close to the conduction band. Similarly, in a P-type semiconductor, the Fermi energy level is close to the valence band. But in a degenerate semiconductor, the doping is so high that in an N-type degenerate semiconductor, the Fermi energy level is even above the conduction energy level. So we are talking about doping levels around 10 to the power of 20 or even higher per centimeter cube. Similarly, in a P-type degenerate semiconductor, the Fermi energy level is even below the valence energy level. So once again, we are talking about doping levels around 10 to the power of 20 per centimeter cube or even higher. And mostly degenerate semiconductors have applications in making contacts, for example, to wide band gap semiconductors, or in making tunnel junctions in multi-junction solar cells, etc. In semiconductors, we have two categories. We can have direct band gap semiconductor, or we can have indirect band gap semiconductors. In direct band gap semiconductors, the minimum of the conduction energy level actually occurs along the maximum of the valence energy level in the EK diagram, where E represents the energy axis and K represents the momentum axis. And we know that generally holes have a tendency to move to the top of the valence band, and electrons have a tendency to move to the bottom of the conduction energy level. So in direct band gap semiconductors, the minimum of the conduction band is aligned with the maximum of the valence band, valence energy level along the energy vector. So any transition, for example, a recombination of electron and hole over here would result in the conservation of energy only and not in the conservation of momentum. So this recombination of electron and hole would result in the emission of photon, and almost all of this energy would be contributed to the emission of a photon. In indirect band gap semiconductors, the maximum of the valence band is not directly aligned with the minimum of the conduction band. So a transition of electron from the conduction band to the valence band would actually incorporate conservation of momentum and conservation of energy as well. So this recombination would actually partially result in the in phonons or lattice vibration, resulting in heating of the semiconductor device and partially resulting in radiative recombination. So generally, direct band gap semiconductors are desired for most of the semiconductor devices, for solar cells, for photodetectors, for light emitting diodes, and for these kind of applications. Consider a p-n junction under equilibrium. Here is the energy band diagram of a p-n junction under the equilibrium, where we see we have a constant Fermi energy level under equilibrium. The Fermi energy level is close to the conduction band on the right side. So it means that on the right side we have an n-type semiconductor. Similarly, the Fermi energy level is close to the valence energy level on the left side, which means that we have a p-type semiconductor on the left side. Now, under thermal equilibrium, without going into a lot of details, we see a built-in potential barrier when we arrive the equilibrium point. So because of this built-in potential barrier, now electrons would not be able to move from the n-type layer to the p-type layer. Similarly, because we have a built-in potential barrier for holes as well, so holes would not be able to move from the p-type layer towards the n-type layer. Under forward bias, which means that we apply positive potential to the p-type layer and negative potential to the n-type layer, and according to this simple formula, energy is equal to minus charge times voltage. The side to which we apply positive voltage would be, its energy levels would be dragged down. So here we apply positive potential to the p-type layer. It means that as compared to the equilibrium, now all these energy levels, the conduction energy level, the Fermi energy level, and the valence energy level on the p side would be dragged down, and now we don't have a constant Fermi energy level. And because of this, this potential barrier is now reduced, making it easier for carriers to flow across the depletion region, across the metallurgical junction. So under forward bias, it becomes easier for electrons to move towards the left, and it becomes easier for holes to move towards the right, towards the p-type layer, resulting in flow of carriers corresponding to a particular current in a p-n junction. However, under reverse bias, we know that this potential barrier further increases, making it more difficult for carriers to move across this p-n junction, to flow across this metallurgical junction. But we still say that we still have a leakage current under reverse bias. So now the point is, where does that leakage current come from under reverse bias? We know that under reverse bias, we apply positive potential to the n-type layer and negative potential to the p-type layer. Applying positive potential to the n-type layer means that the energy levels on the inside would be dragged down. We have this big barrier for majority carriers to flow across the junction. However, we know that in an n-type material, the majority carriers are electrons, but we still have some minority carrier holes in n-type semiconductor. Similarly, in a p-type semiconductor, the majority carriers are holes, but we still have some minority carrier electrons in a p-type semiconductor. So this positive terminal is going to attract these electrons, and the negative terminal is going to attract these minority carrier holes, resulting in a minority carrier leakage current across this p-n junction diode. Although this current is not high, it's in the nanoamps or picoamps range, depending on the quality of the semiconductor device and also depending on the band gap of the semiconductor. But still, some reverse bias current flows under this configuration as well, which we can also see from the IV characteristics of a p-n junction diode. Under forward bias, when we arrive at the built-in potential point at the turn-on voltage point, there is a drastic increase in the current versus voltage. However, under reverse bias, we have some reverse leakage current equal to reverse saturation current times exponential of the applied voltage divided by thermal energy minus 1. Now, let us start talking about the light emitting diode. Now that we understand the basic p-n junction diode and its operation under forward bias and reverse bias, we will dive deeper into the discussion of light emitting diode. So here is a basic configuration of a light emitting diode, where we have a p-n plus layer. N plus means heavily doping and p means lightly doped p-type layer. So here we see that the Fermi energy level is much closer to the conduction band as compared to the Fermi energy level for the lightly doped p-type layer, which is a little bit farther from the valence energy level. Now, as we already know from the discussion of the p-n junction diode, that under thermal equilibrium, we will have a potential barrier for carriers to flow across this metallurgical junction. However, under forward bias, this potential barrier is reduced, making it easier for carriers to flow across this junction. So now electrons can easily flow towards the left, towards the p-type layer, and holes can easily flow towards the right, towards the n-type layer. And across the metallurgical junction, these carriers are directly aligned with each other. So at this metallurgical junction in the depletion region, the electrons and holes actually get an opportunity to recombine, resulting in the emission of photons corresponding to the band gap of the semiconductor. And we see the same phenomenon over here, electrons moving towards the left, holes moving towards the right. Inside the depletion region, they get an opportunity to recombine, resulting in the emission of photon. Here is another configuration of light emitting diode. It's called planar surface LEDs, in which we have an N plus substrate, and then we grow an epitaxial N plus layer on top of that, and finally an epitaxial p-type layer on top of that. So with the application of voltage to the contacts under forward bias, as we already discussed, it's going to result in the flow of carriers across the junction, and then these carriers recombined, resulting in the emission of photons. So generally this top layer, the p-type layer, is thin enough so that these generated photons can easily escape the semiconductor device and move into the environment. Here is another configuration. In this configuration, we have the same N plus substrate, and then we have the N plus epitaxial layer grown on top of that. But the p-type layer is not epitaxially grown. It's actually grown either using diffusion or ion implantation followed by annealing to recover from damage and to activate the dopants. And then we have contacts, and then current flowing through this would actually give an opportunity to electrons and holes to recombine, resulting in the emission of light, which escapes through the top thin p-type layer. Consider this light emitting diode configuration in which we have a substrate, an N+ layer, and p-type layer. And recombination of electrons and holes would result in the emission of photons. Now these photons now have to escape this semiconductor device structure, this LED structure. But this escape of photons actually depends on the angle of these photons hitting this interface of the semiconductor device and the external environment, which in this case could be air. So if the angle of these incident photons with respect to the vertical axis is smaller than a certain critical angle, then these photons would escape the light emitting diode and move into the outer environment, which in this case is air. However, if the angle of incidence of these photons is greater than some certain critical angle, then they are going to be reflected back into the structure, resulting in lower external quantum efficiency of the device. So one solution to cater for that is to grow a domed semiconductor light emitting diode structure, so the light gets an opportunity to escape in different directions. Another solution for that is to encapsulate this light emitting diode with a plastic dome or with an epoxy dome, and this results in better escape of photons from the light emitting diode structure, because the refractive index of plastic actually closely matches with air as compared to the refractive index of semiconductor, for example silicon, with air. So this matching of the refractive indices actually makes it convenient for light to escape from the light emitting diode configuration. Now consider two layers. N1 represents the refractive index of the semiconductor, for example silicon, and N2 represents the refractive index of the second medium in which light needs to escape to. For example, the second medium could be air, and here is the interface of the semiconductor and the outer environment. So if this incident light generated as a result of the recombination of electrons and holes, this incident light makes an angle theta I with respect to the vertical axis. If this theta I is smaller than a certain critical angle, then this light would escape the semiconductor into the outer environment. It's going to be transmitted to the second medium. However, if this incident angle is equal to the critical angle, then light is going to travel along the surface of the semiconductor. And if this incident angle of light is greater than the critical angle, then this light is going to be reflected back into the light emitting diode structure. The critical angle is defined by Snell's law, and this critical angle is equal to sine inverse of the refractive index of the second medium divided by the refractive index of the semiconductor. So here is a practical example. Consider this configuration in which we have a light emitting diode structure, and so we call this medium 1, and the second medium is air. So the critical angle for this would be equal to sine inverse of the refractive index of air divided by refractive index of this semiconductor, where the semiconductor is silicon, and here are the refractive indices of the two. So the critical angle comes out to be 15.25 degrees. If the angle of incidence of these photons is greater than 15.25, then they are going to be reflected back into the semiconductor structure. Now consider another configuration in which this light emitting diode is encapsulated by a plastic dome. So for this, first light has to escape from the semiconductor into the plastic dome, and for that the critical angle comes out to be 21.61 degrees, which is much greater as compared to the first configuration. And then light has to transmit to the outer environment, to the air from the plastic dome. And the critical angle for this light for moving from the plastic to air comes out to be 45.58 degrees. So we get a much wider critical angle if we encapsulate the semiconductor structure using a plastic dome, because it results in matching of the refractive indices of the silicon to the plastic dome to air. The quantum efficiency of any device is generally equal to the output divided by input. In case of light emitting diode, the output is optical and the input is electrical. And its external quantum efficiency would be equal to the optical power divided by electrical power into 100%, where I represents current and V represents voltage. Now in this slide I have given a comparison of the efficiency of light emitting diode configurations in which one structure is not encapsulated and the second structure is encapsulated with epoxy. And using this simple expression, we find out that the quantum efficiency of this configuration, which is encapsulated with epoxy, or we can encapsulate it with plastic as well, is 2.5 times higher as compared to this configuration which is not encapsulated. So it's a good idea to encapsulate our light emitting diode structures, and that is what we see in practical real life LEDs. There are different light emitting diode material possibilities in order to achieve light in different wavelength ranges. For example, aluminum gallium nitride gives us light in the ultraviolet range below 350 nanometers. Indium gallium nitride, depending on the indium content to gallium content, gives us light in the range of approximately 350 nanometers, which is ultraviolet, to approximately 570 nanometers. So it gives us light in the ultraviolet to blue to green range, but currently research is under progress. So people are working on yellow light emitting diodes based on indium gallium nitride material as well. Then aluminum gallium indium phosphide results in light in the approximately 570 to 620 nanometers, yellow to orangish light. Aluminum gallium arsenide gives us light in the red to infrared range, and indium gallium arsenide phosphide results in light emission in the infrared range. And then this wavelength range around 1.4 micrometer, 1.5 micrometer actually is suitable for communication purposes. We previously talked about the basic N plus P light emitting diode configuration. The problem with that configuration is that it does not result in a high light intensity. There is low emission of light from the basic N plus P structure. So in order to achieve higher light intensity or higher emission of light, we need to grow more complicated structures. And one example of that would be double heterostructure N plus P LEDs. In double heterostructure, we have a narrow bandgap material, for example, gallium arsenide, for which the bandgap is 1.4 electron volts. And this narrow bandgap material is sandwiched by wide bandgap materials on either side, for example, aluminum gallium arsenide, which we can configure to achieve a bandgap of 2 electron volts. Under thermal equilibrium, looking at this energy band diagram, we see that we have electrons in the conduction, plenty of electrons in the conduction band on the left side in this N plus layer, and we have plenty of holes in the aluminum gallium arsenide p-type layer and also in the gallium arsenide p-type layer. But these electrons and holes are not directly aligned, so it's not going to result in the recombination of a lot of carriers. However, under forward bias, when we apply positive potential to this side, we drag down the energy levels on this side. So we actually reduce this barrier for electrons, and now electrons can easily move to the gallium arsenide layer as well. And now in this case, we have plenty of electrons and holes which are directly aligned across the band gap of this structure, resulting in a high number of recombination of electrons and holes, giving us more number of photons for light emissions. Then we can grow even more complicated structure. For example, here I have here is the layer structure diagram of one of the LED structures that I personally designed in Silvaco TCAD software, and it is gallium nitride based, in which the outer layers are N-type gallium nitride and P-type gallium nitride. And the active region which gives us light is composed of indium gallium nitride with a 16.5% indium content, and then this barrier layer, and then another indium gallium nitride layer which has a composition of indium content of 27%, and then aluminum gallium nitride electron blocking layer. This indium gallium nitride layer results in the emission of blue light, and this indium gallium nitride layer, which has indium content of 27%, results in yellow light, and the combination of blue and yellow light actually results in white light. So I actually tried to design gallium nitride based LED resulting in white light. Here is the Silvaco TCAD diagrams of the same structure, and here are the layer descriptions, the layer thicknesses and doping concentrations of each layer in the structure. Here is the energy band diagram of the structure under thermal equilibrium, where on the right side we have N-type gallium nitride layer, on the left side we have P-type gallium nitride layer, and here is the active region, where we have one indium gallium nitride layer and another indium gallium nitride layer. These are the active layers, forming quantum wells. Now, under thermal equilibrium, we have plenty of electrons in both quantum wells, but there is a big barrier for holes to move towards the quantum well. However, under forward bias, then holes get an opportunity to move towards the right as well, to move into the quantum wells, and then we have plenty of electrons and holes available across the quantum wells for the indium gallium nitride layer, recombining, resulting in the emission of photons. Here is the IV characteristic of the same LED structure. Just like a PN junction diode, this LED also has a turn-on voltage for gallium nitride. Gallium nitride has a band gap of 3.4 electron volts. So for a gallium nitride based LED, the turn-on voltage would be around this voltage as well, around 3.1, 3.2 volts. Here are the spectral power distribution of this LED structure, of the gallium nitride based LED structure. So I actually designed this LED in such a way that at lower voltages it's going to give green light emissions around 540 nanometers, at medium voltages, or at, for example, 4 volts, it's going to give both blue light and green light as well. However, at high voltages, it's just going to give blue light emission around 440 nanometers. And then I applied the same concept to achieve another structure resulting in blue and yellow light emissions, where blue and yellow light emissions combine to form white light. Here is the meshing, and once again the layer description, some figures from Silvago TCAD. Don't want to go into the details. Light emission characteristics. We already discussed the distribution of electrons in the conduction band and the distribution of holes in the valence band. So from that we found out that the holes are not actually exactly at the valence band. There are certain distribution where we see peak distribution is close to the valence band, but it's not exactly at the valence band. Similarly, electrons have some sort of distribution in the conduction band, and its peak is approximately half kBt away from the conduction band. So when recombination of carriers occur, the emitted light wavelength would actually not just exactly correspond to the band gap of the semiconductor. The energy of these photons, the emitted photons, would be equal to the band gap of the semiconductor plus half kBt, where we see peak distribution of electrons is half kBt away from the conduction energy level. So generally we say that the energy of the emitted photons correspond to the band gap of the semiconductor, but to be more precise, we actually have to consider this distribution of carriers, which is half kBt away from the conduction energy level. So generally, with increase in temperature, the band gap of a semiconductor shrinks or decreases. So which means that with increase in temperature of the light emitting diode structure, the peak emitted wavelength also increases. For example, consider aluminum gallium arsenide LED, which has a peak wavelength at 822 nanometers. So at room temperature, we see its peak wavelength is 822 nanometers. But with increase in temperature, its peak wavelength increases to 837 nanometers. And with decrease in temperature to minus 40 degrees C, its peak wavelength decreases to 804 nanometers. Another terminology in light emitting diode is line width. So consider 50% amplitude points along this spectral power distribution of the LED structure. Here are the 50% amplitude points. The difference in wavelength between these points is called the line width, which in this case is 40 nanometers. Generally, a narrow line width is more desired for light emitting diodes. The narrower the line width, the closer it is to laser properties. How do we calculate the line width? So generally here is a relationship for wavelength equal to C divided by V, or Hc divided by the energy of the emitted photons. Now take the derivative of the wavelength with respect to the energy of the emitted photons. We have this relationship, and then for small changes, delta lambda divided by delta EPH is equal to the derivative of wavelength versus the energy of the emitted photons. So assume that the energy of the emitted photons have a distribution around 3 kBt away from the conduction and valence energy levels. So if this EPH is equal to 3 kBt, then replace this value of EPH with 3 kBt, we finally get to this relationship where this line width delta lambda is equal to lambda square times 3 kBt, where kB is the Boltzmann constant, T is the temperature, divided by hc. H is the Planck's constant and c is the speed of light. So if our wavelength is 870 nanometers in the infrared light range, then the line width comes out to be 47 nanometers. At a wavelength of 1300 nanometers, the line width comes out to be 105 nanometers. At a wavelength of 1550 nanometers, the line width comes out to be 149 nanometers. So we considered the line width. Now let us calculate the wavelength variations, the peak wavelength variations. So in the previous slide, delta lambda actually represented the line width, but in this slide, slide number 42, delta lambda actually represents the peak wavelength distribution, or the change in the peak wavelength with respect to temperature. As we already discussed that with increase in temperature, the wavelength, with increase in temperature, the band gap shrinks and the wavelength increases, and vice versa. So consider gallium arsenide based LED. Gallium arsenide has a band gap of 1.42 electron volts at room temperature, and the temperature coefficient, the derivative of the band gap with respect to temperature is this value, electron volts per Kelvin. So we need to calculate the change in the peak emitted wavelength if the temperature changes 10 degrees C. So we know the relationship for wavelength. If we ignore the distribution of carriers away from the conduction and valence energy levels, is equal to Hc divided by the band gap of the semiconductor. Now take the derivative of the wavelength with respect to temperature, we get to this relationship. And dEg divided by dt is already given in this example. So putting the value of this and the band gap value and the Planck's constant and the speed of light, the derivative of lambda with respect to temperature comes out to be 0.27 nanometers per Kelvin. For small changes, we can say that delta lambda divided by delta t is approximately equal to derivative of lambda with respect to temperature. So putting in values into this, we already know the value of d lambda divided by dt, already calculated, and then the change in temperature in this example given as 10 degrees C or 10 Kelvin. Since it's a change, so we can write it down in terms of Kelvin because all the calculations are in terms of Kelvin. So it comes out to be 2.8 nanometers. For a 10 degrees C change, we see 2.8 nanometers change in gallium arsenide based LED. So which means that with increase in temperature, the peak wavelength is going to shift towards the right. It's going to increase by 2.8 nanometers. And with the decrease in temperature by 10 degrees C, it's going to move towards the left by 2.8 degrees C. Consider, for example, aluminum gallium arsenide based LED. Its wavelength is 820 nanometers at 25 degrees C. With increase in temperature, its band gap shrinks and its wavelength increases to 840 nanometers at 85 degrees C, while its peak wavelength decreases with decrease in temperature to 800 degrees C at a temperature of minus 40 degrees C. Here I have listed different material-based light emitting diodes. For example, gallium arsenide. It is direct band gap semiconductor material. Its wavelength is in the range of 870 to 900 nanometers. So it actually results in infrared LEDs. And then we could have aluminum gallium arsenide. Indium gallium nitride is more famous for blue light emitting diodes. And then gallium nitride is famous for green light emitting diode. One application of light emitting diode is white lighting, because we generally use white light for lighting purposes. And white light can be achieved by a combination of either blue and yellow light or by a combination of red, green and blue light. So one way to achieve white light is to use a blue light emitting diode and then grow a yellow phosphor on top of that, where phosphor actually is cerium doped yttrium aluminum garnet. So this blue LED results in the emission of blue light, and then this blue light, part of this blue light actually pumps the yellow phosphor, resulting in yellow light emission, and then the combination of blue and yellow light gives us white light. Or another possibility is to have an ultraviolet light emitting diode and then grow 3 phosphors on top of that, red, green and blue phosphors. So the ultraviolet light pumps the red, green and blue phosphors, resulting in the emission of red, green and blue light, and then the combination of these 3 lights result in white light. And here is an example of blue and yellow light resulting in white light. Here are a few homeworks for you. Please solve the homeworks and submit it by the next lecture. That concludes the lecture, and I will see you next time, inshallah.